Okay, so our next speaker in the ASIC track is Andrew Gardner of ARM. Andrew is a principal design engineer. Title of his talk is FPGA Accelerated IP Validation, and it is in the ASIC track rather than the FPGA track, because I think, as you're probably well aware, ARM are mostly about ASICs, so it's a verification of ASICs using FPGAs. Andrew is responsible for hardware accelerated IP validation platforms at ARM, and previously led the FPGA group responsible for the delivery of multi-FPGA implementations of CPU, interconnect fabric, and systems IP. The primary goal being IP validation. Thank you.
Hi. So perhaps this is going to be a little bit different to a lot of the other talks that we've had today. So rather than talk about system Verilog and assertions, what we're going to talk about is a hardware platform and essentially a methodology that sits around it to validate ARM's IP. I guess that, is that better? Okay. So I guess the title of this should perhaps have been FPGA Accelerated System IP Validation, because we're not validating discrete IPs in FPGA, it's full system level validation. So we're using FPGAs to scale, if you like, to be able to achieve the sort of throughputs that you just can't get in simulation and emulation. So the problem we had in ARM was that simulation and emulation simply don't scale at the system level. You look at the cost per cycle of these systems. In simulation, you need your very large compute clusters. Emulators, although very capable and very good for debug, are extremely expensive and difficult to implement on scale. So what we've done with commercial off-the-shelf FPGAs is to build in parallel multiple platforms where these designs, primarily ARM CPUs and interconnects, are implemented at an SoC level, if you like, capable of booting an OS. And what we do is we run on multiple platforms, speeds approach around about 10 megahertz in multi-FPGA systems. Okay, around about 10 megahertz in multi-FPGA systems, and we run in parallel with their stimulus across multiple platforms to try and achieve cycle counts comparable to running silicon for extended periods. The target for FPGA typically is by REL on an IP. We aim to run at least 1 month's worth of stimulus, so about 2 to 3 petacycles worth of stimulus through the platform. We provide platforms with high levels of debug visibility. So a lot of people view FPGAs as simply a black box. It's great, you can run it faster, but you just can't see what's going on in there, and you certainly can't debug. That has changed in the last few years. There are a number of FPGA debug technologies available from the likes of Synopsys and Mentor Graphics, and some third parties as well, that allow you to have debug visibility in excess of 1,000 signals per FPGA at speed, so running at 10 megahertz. So what we've done is taken all of this stuff and built it into a farm infrastructure. So this is a basic diagram of what we've got with each of the platforms. So at the center of everything we have the farm board, so that'll be your multi-FPGA platform, and round about that platform we've got things like the servers, which are used to communicate with them. We've got hardware logic. Let's go back one. So we've got hardware logic analyzers there, so that's the FPGA debug solution. So that involves taking the signals, serializing them, extracting them from the FPGA platform, and building the debug environment around that. We've also got our own ARM's DStream debugger in here as well. So software engineers can sort of get in stop cores, they can single-step code, they can look at instruction trace streams. And around about the rest of this, what we've done is, I guess anyone who's used an FPGA platform in the past, and perhaps used to having one on a desk, you can do things, you can power cycle it if it locks up. So what we've done is taken away the FPGA platforms away from people's desks and built them into an enterprise-like structure. So to enable that, we've built customized sort of power and reset controllers that allow you to do everything that you would on the desk level. And wrapped around all of this environment, what we've got is an automation system. So having a simple module file that you can load that enables you to issue commands down to the FPGA platform to load test stimulus, to connect to your debuggers, both the hardware logic analyzer and software debuggers, and do everything that you would on a desk-based system. It also enables you to automate the sending of the payloads into the platform. Okay, so we've got the infrastructure, so that we found there's three main requirements that you need to satisfy to be able to run effective stimulus in FPGA systems. First thing you need is the right system in here. You need to be able to create a stressful setup. You need to be able to create scenarios that are like real-world scenarios in FPGA. If you try and build a system, typically it's difficult to achieve the sort of clock frequencies that you can achieve in a real-world system. That can mean that the types of stress and situations and the bugs that you'll see in FPGA may be real bugs, but may be highly unlikely to be observed in a real-world system. Next, you need the right stimulus. The stimulus that runs on the platform needs to make best use of the available resources. Initially, a lot of the engineers who ran on the FPGA platforms were generating offline stimulus, loading it into the platform, running that. So we've now replaced that with self-generating stimulus on the platform, so we've now got 24/7 use of the FPGA hardware. And finally, you need the right debug in the mix as well. That debug engineers, especially verification engineers used to simulation and emulation, simply won't use the platform. So I think, yes, one thing that's good to note is that a rarely observed is rarely fixed. So with the right system, what you need to be able to do in the FPGA platform is to repeatedly observe the same failure scenarios. To do that, you need to have a cycle-accurate system. You need to have all clocks typically running synchronously. You can spoof asynchronous clock domains using things like clock-enabled techniques. Ideally, you need to have representative clock rates as well in the system to get good coverage and to basically create the real-world stress that you need. External stimulus is a problem as well. So if you've got someone who wants to mount a file system through the FPGA, through the payload running on the platform, that's not achievable really in a cycle-accurate system. You need to remove that sort of interaction. And key as well, we've integrated a lot of verification IP into the system as well. Things like protocol checkers, key to identifying bugs automatically. For memory models, we found that the DDR is a problem. With DDR, you've got things like refresh cycles that aren't predictable. You've got an asynchronous clock domain going from the FPGA into the real world. So what we've done is replace that with a model which sits in the path between the sort of your design in the FPGA and the real world DDR interface. We do make limited use of coverage checkers, but not in any sort of formal way. It's really just to give feedback to the designers of the payloads. That's something we need to look at in more detail in the future, I think. And I think critically, one of the biggest areas is irritators in the system. So we've added those, whether that's to delay responses to memory accesses or whether it's to actually inject traffic into the system. We found that those significantly increase the numbers of bugs that you can find. Okay, so this is a typical ARM-based design. So this is a dual cluster compute subsystem with multiple CPUs inside each cluster, so big and little concept. So the systems we typically put today, we've got about 6 CPUs between the two clusters, private L1 cache, shared L2. Then we've got a CCI cache coherent interconnect externally to maintain cache coherency between the L2 caches in each of the clusters. And then we've got the rest of the components you really need to make up a system that's capable of booting an OS. And the blocks in red that you can see, unfortunately it's not too clear here. We've got the things like the irritators in here. So here we've got traffic being injected into each of the coherency ports of the CPU clusters. We've also got coherent traffic being generated into the interconnect here to create stress, try and flesh out any bugs in the CCI. And around the system we've got multiple monitors looking at the traffic, so that this provides feedback to the stimulus running inside the CPUs as to what's going on in the system. And we've also got things like memory models around there to remove things like the DDR refresh cycle problem. Okay, so I mentioned we need in terms of stimulus, we need to make the best use of every cycle on the platform. We use a mixture of in-house stimulus and external third-party tools on the FPGA platforms. So it's a mixture of pure random stimulus that's generated on the system, by the system, and it's directed random testing. We find that the highest bug find rate of all of them is with the complete random stimulus. So that typically takes about 98% of the time generating the stimulus, and about 2% of the time just running the test sequences that are generated. We found over the golden summary at the end, we found a significant number of bugs using this. I think the main thing about the stimulus is that it plays into this idea that you can create a platform where you can replay a bug. You find a problem, you can then you can go in and debug it next time. You can move your debug resources around, replay that failure time and time again. Initially, the problem with the debug is that we'll have platforms that will be up and running for maybe a month at a time, and a month into running stimulus, you'll find that bug. These tools that we have enable you to take that month's worth of stimulus and condense it down into a test case that will run in a few milliseconds, and you can repeatedly run that one and then refocus your debug resources. Okay. In terms of debug, that's probably the biggest problem we've had to solve with the FPGA platforms. We had to provide an environment that enabled engineers that were used to running on simulation and emulation, the platform that they would find acceptable, and we build up acceptance within ARM of this technique. So we've used a third-party tool to provide a visibility of at least 1,000 probes per FPGA. What we've done is developed internally a tool called Tarmac. So Tarmac allows you to probe internal registers inside the CPUs. You can extract that data, post-process it offline, and you can actually turn that into a human-readable instruction trace stream. It's quite valuable in this case because typically these platforms are being developed and brought up before all of the debugger and software infrastructures around to support it. So that gives you a good starting point. But the problem is just being able to see an instruction trace stream typically isn't enough to debug what's going on inside the FPGA. So what you need to do is provide techniques and methods for the end users to take that debug that's focused in on those Tarmac registers and then move it to where they want in the design. So one of the key features of the FPGA infrastructure is that we've taken the debug out of the hands of the FPGA engineers and really placed it into the hands of the verification engineers. That's helped greatly to increase the acceptance of FPGA, but the productivity obviously has gone up significantly, and it's enabled the group to scale significantly. Go into a little bit more detail. So we've got two types of debugs. So I've talked about probing. So we've got 1,000 signals per FPGA. They stream offline. So we serialize the data. It comes out over LVDS to a central hardware logic analyzer, where we've got about 8 gigabytes of DDR memory. Running at 10 megahertz, we can see about 0.8 of a second of real-time debug data. Over the whole platform, that will be around about 6,000 signals at 10 megahertz. And you can create your trigger events for this on the fly and have them at any amount of pre or post trigger you like in the system. But we found that with just straight probing, it was debug turnaround times are very high. So we've got another technique that uses a technology called readback that's built into the Xilinx FPGAs. So essentially it's a scan shift technique. So what we can do is, using the hardware logic analyzer, we can send the clock enable into the platform, and we can stop all the clocks to the design. We can scan shift the entire design, every register, every memory inside, and then as soon as that's extracted, apply another clock cycle, build up a bigger picture of the design. So this has been particularly powerful in sort of deadlock scenarios, where we've been able to, once the system's got into this locked up state, we've been able to extract very meaningful deep waveforms that enabled that in a single turn of the debug handle, if you like. The engineers have been able to sort of get to the root cause of the problem. So as I said before, we found significant numbers of erratum in pre-released IP. I think the total now is up to around about 50. That's 50 bugs that wouldn't have been found in simulation or emulation. We've also found erratum in released IP. So we came to this, I guess, just after Cortex A9, where there were a significant number of post-release erratum. And we sort of started running on that and some legacy processors. Using this platform and this technique, we've managed to identify bugs that were never observed in silicon, even though they've been in the market and in the field for years. We managed to get to find the bugs in the FPGA platform, but also root cause them and debug them. So that's now FPGA-based testing with this methodology. It's now a formal part of the IP validation system at ARM. And just a little bit about next steps. So what we talked about with the system and the verification IP and the stimulus running on the platform, we are now going to take that and put that into silicon and extend this testing even further. So we're going to see orders of magnitude increase in the number of cycles, and we should see years of stress running on the IPs before the REL date. So any questions?
Yeah, thank you, Andrew. Thank you. We have time for just maybe. Ashish, you've moved.
Yogesh from Ericsson. Basically, how do you reduce the impact of build time of FPGA? Because turnaround time can be significantly high. And second, FPGA's optimized design RTL, how do you manage to reconstruct signals for full visibility?
Okay, and so in terms of the build time, so FPGAs are notoriously long to build. We do suffer from the same problems. So that the initial image, the system that you showed you, the compute subsystem here, that's built, the entire RTL is stitched by one engineer. The system's then taken, partitioned, implemented in an FPGA platform, tested, brought up with the software and an operating system by that one engineer. It takes about 3 months. But the flows that we've built around it, and things like the probe retarget flow that enable engineers to move the probes around, that removes a lot of the need for the engineers to rebuild the images, and automating that flow has been a huge help. Incremental updates to this, so when we see a CPU update, take around 24 hours to turn around. So that's just being very careful with how you partition the design and trying to ensure that in a multi-FPGA system that you don't have where you're updating a CPU, try and constrain it to a single FPGA. If you know that IP is going to be updated regularly, it makes the whole process a lot simpler. And the second question, sorry? Okay, so okay. So the tool flow that we have is heavily integrated into the full implementation flow for debug. So it's aware of the optimizations that happen through synthesis and place and route. So it builds up what we call a runtime database. So that's then loaded by the engineer who wants to run on the platform. So they use a scan technique to dump the signals that can then back annotate those signals all the way back down to RTL. We do see a certain loss in visibility, but we tend to see between 94 and 97% RTL visibility of what's running in this platform.
Okay.
Yes. Yeah, we use Verdi.
Okay. I think that's it. Oh, one last question from.
What kind of performance are you able to get using this?
In a multi-FPGA system, because you need to partition the design, you just need to serialize data. You've got FPGAs with 1,000 pins on them, and you're trying to take 20,000 signals across there. That need to serialize data restricts the speed of a multi-FPGA platform to around about 10 megahertz. If you've got single FPGA clock domains, in theory they can run as fast as you like, but because you've got this 10 megahertz limitation at one point in your system, you want to scale every clock up or down from that 10 megahertz. So you'd say around about 10 is a good.
Yeah, and it looks like you're using the Xilinx readback technology.
That's right.
Which is very slow, right? So
readback slow, yeah. So the power of readback is it feeds into this idea of cycle accuracy and the ability to take a payload and replay it multiple times. If you can replay that payload, after a few iterations, you get to know the point, even if it's looking at a cycle count register, you know where the debug point in time is going to occur. So that then gives you the point at which you would switch on your clock enables and start to build up this picture of the design. But as I said, the biggest use of it by the verification engineers has been in things like deadlock scenarios, and they are, it doesn't matter so much.
Thank you. Thank you very much. Thanks, Andrew. Thank you. Just trying to see if there's any more questions. Thank you.